How are you today?
Good, how are you?
Good. So what are we doing today?
We're just gonna do some a little bit more polar curves because our polar curves and stuff.
Okay. What do you got?
All right. So this question asks for the domain, range, line of symmetry, and maximum R value for R equals 7 minus 2 cosine theta.
And what do they want here?
The domain and range, line of symmetry, and maximum R value.
Okay. What's the domain?
The domain is, let me see, so
which variable are we talking about when we talk about domain?
the x variable.
Which variable in this problem?
Oh, the theta?
Okay. So what can theta be?
Theta can be 0 to 360.
It can be anything. It can be negative infinity to infinity.
Okay.
All reals. Okay.
All right.
About range. What can R be?
R can be I don't know.
To figure out what R is, figure out what the maximum that can be is and what the minimum that can be is.
The maximum that can be is 2.
Okay, so that would make 5 is the minimum that R could be.
Is -2.
Which makes the maximum for R 9. Correct? In other words, if that's -1, then this whole thing is -2. 7 minus a -2 is 9. All right. So what is the line of symmetry? In other words, if I'm graphing this, and I'm graphing some cosine function, what is this line right here?
The line of symmetry is the origin, right?
Well, let me think about this for a moment. I was thinking about this incorrectly. Let's do the maximum first. We've already got the maximum. That's 9.
Yeah.
So, let's see. If we were talking an xy function, then the line of symmetry would be y equals 7. Right? In other words, if I'm talking x equal -2 cosine theta plus 7, the line of symmetry is 7. But we're in polar coordinates. Do you have answers on these?
No.
Hold on a moment. I'm thinking the line of symmetry is still 7, but let me see if I'm missing something here. Let me look up polar coordinates in my book and see if there's a different line of symmetry, or if you know of any. I'm not familiar with line of symmetry on polar coordinates. And I'm looking in my book right now, and I don't see anything. Hold on, symmetry. There's tests for symmetry for polar graphs. There's a test for symmetry about the x-axis, about the y-axis, and about the origin. But I don't see anything for testing for a line of symmetry. I have an example here, test for symmetry. Maybe we can get to the bottom of this here. I have a function here that is r equals 4 sine of 3 theta. And there are tests for symmetry. And the question is there symmetry about the x-axis? Or is there symmetry about the y-axis, or is there symmetry about the origin? As far as a line of symmetry for a polar function, I don't know how to do that. And going through the other would take like 15 or 20 minutes, and I'm not sure that the other is what you're looking for. Yeah, there is nothing about line of symmetry in my book. However, I'm thinking that looks an awful lot like y equals minus 2 cosine theta plus 7, and in the y theta coordinate system, the line of symmetry would be 7, y equals 7. In the polar coordinate system, I'm not sure what they're looking for a line of symmetry. This seems to be, hold on a moment, this looks to be a cardioid. Well, this might illuminate things. If I have this function, I can graph this. You still there, Lucas?
Yeah.
Okay. I can graph this in two ways. In the polar coordinates, it looks like this. And in rectangular coordinates, it looks like this. Well, notice this is the cosine curve moved up by 2 units. So, in other words, this is the XY graph. This is the polar graph. The polar graph, I would have to say the line of symmetry is y equals 0, right?
Yeah.
In other words, if we were looking to find some sort of symmetry there, there is symmetry about the x-axis, or theta. Yeah, I guess it's correct to label that theta. But there's symmetry about theta equals 0. So if I had to find a symmetry here, it would be theta equals 0. And over here, if I had to find a symmetry, well, if I graph that as y equals 2 plus 2 cosine theta, the line of symmetry goes right through there, which is plus 2. So I don't know if that's helpful or not, but I think it should be, because I got to think that one of these two things is the line of symmetry. There is no other line of symmetry on the polar graph of this thing. In other words, the only line of symmetry on the polar graph is the horizontal axis. This is not a line of symmetry. This is not a line of symmetry. The only line that is symmetrical and everywhere is the x-axis. And the function you gave me is 7 minus 2 cosine theta. That's pretty much the same format as that. So I'm sure that it is a cardioid, and that its xy graph would be this. So I think we can talk about it in the same way we can talk about this. I could certainly graph this on Wolfram alpha, and we would see that it's a cardioid.
Yeah.
All right, what else you got?
All right, the next one is find an equivalent equation in polar coordinates in which 2x plus 3y equals 6.
What are the identities between polar and xy coordinates?
Isn't it like x equals cosine theta and y equals sine theta?
X equals r cosine theta.
Okay.
Y equals r sine theta. Now let's talk about that for a moment, why that's the case. There's theta. There's x. There's r. Cosine of theta equals x over r.
Yeah.
Therefore, x equals r cosine of theta. Same reasoning, that's the y-coordinate. Sine of theta equals y over r, or y equals r sine of theta. And the last identity is r squared equals x squared plus y squared, based on this same picture. Okay? So, let's just substitute. We got 2 times r cosine theta plus 3 times r sine theta equals 6. Hold on. That's actually correct. Except we generally, when we're converting to polar, we want an equation that is r equals something. Well, if I factor r out from the left side, I have this. Divide both sides by that, and I have r equals 6 divided by 2 cosine theta plus 3 sine theta. And there should be your answer. Now, that doesn't look right to me, because what we're looking at is the equation of a straight line. And the equation of a straight line is always theta equals something. In other words, one of the reasons we like polar over rectangular is that if I have the equation of that line, which is y equals x, in rectangular, that's also theta equals pi over 4 in polar. And in fact, if I make that y equals something else plus x, in other words, if I move that to there, so it's y equal x plus 3, which is the situation we're looking at, a straight line whose y-intercept is not 0. That's going to be a much more complicated polar equation. This equation is not so straightforward in polar coordinates. So coming up with an answer like we did is perhaps very correct. I'm looking at a problem in my book, converting from rectangular to polar, and the rectangular equation was the equation of a circle, x minus 3 squared plus y minus 2 squared equals 13. That's the equation of a circle with radius square root of 13, centered at 3, 2. And when they go through the procedure to convert that to polar, they end up with in other words, they end up with a function of cosine theta and sine theta. Well, when we took our straight line and converted it to polar, we ended up with this. R equals 6 divided by 2 cosine theta plus 3 sine theta. So, I could have made a mistake there, but I don't think so. So all I did was plug in r cosine theta and r sine theta, factored out the r. Yeah, no, that should be the answer.
The 6 over 2 cosine theta
Yeah,
is right?
6 over 2 cosine theta plus 3 sine theta.
Okay. Yeah.
Might be a prettier way to write that, although I can't right off hand think of anything that'll make that look nicer.
All right, the next one I have is it's that multiple choice, and it says choose the one alternative that best completes the statement or answers this question.
Okay.
And it's y equals 6. and the options are r equals 6 cosine theta, r equals 6 cosecant theta, r equals 6 secant theta, and r equals sine theta. 6 sine theta.
Okay. Well, we're talking about a straight line through that coordinate, and we'll choose our identities. Y is equal to what?
Y is equal to r sine theta.
Huh?
Yeah.
So R equals 6 divided by sine theta.
So it's cosecant theta.
Correct.
6 cosecant.
Correct. You got it.
Okay. All right.
Now, we can continue to go through yours, but I do want to point out an extra identity. In other words, we've got x equals r cosine theta. We got y equals r sine theta. We got x squared plus y squared equals r squared. The one identity that's the most confusing is theta. Well, theta is the inverse tangent of y over x. If x is greater than 0. Theta is the inverse tangent of y over x plus pi if x is less than 0. And the reason I point this out is because this is fairly strange. You don't run into this very often in mathematics. And they may not even have taught it to you like this. But this is the best way to remember it. What's theta equal to if x is equal to 0?
It's equal to I don't know, sine.
Pi over 2. The tangent of pi over 2 is infinite. So when I make x equals 0, this quantity becomes infinite. And when I take the inverse tangent of infinite, I get pi over 2, or minus pi over 2, or 3 pi over 2. I get pi over 2 plus pi, plus multiples of pi. Okay? But this part right here, I'm not sure when it's going to come up in your problems, but I'll bet it's a factor here shortly. What's the next problem you have?
The next problem I have is eliminate the parameter.
Okay.
And it's x equals p plus 4 and y equals p squared.
If we eliminate the parameter, we can end up with an equation that is just x and y. The way to do that is to solve each one for t and let equals the other. In other words, in this case, t equals x minus 4. In this case, t equals plus or minus the square root of y. Well, this t has to equal that t. So x minus 4 equals plus or minus the square root of y. We want to get rid of the plus or minus. We'll square both sides. Squaring both sides gives us x minus 4 squared equals y. And there's your answer. Notice that that is the equation of a parabola shifted 4 units to the right.
Yeah. All right. I just have one more.
Okay.
X equals sine t.
Sine of t.
Yeah. And y equals 3 cosine t.
Okay. You have to solve these a little different. These are well, let me show you how to solve it, and then I don't know. So we have sine t equals x, cosine t equals y divided by 3. Okay? So if we have those two equations, you can always add equations together. And I can square both of these. If x equals sine t, then x squared equals sine squared of t. And if y over 3 equals cosine of t, then y squared over 9 equals cosine squared of t. Now, adding them together makes a little bit more sense, because we happen to know what sine squared plus cosine squared is. What is it?
Sine squared plus cosine squared is tangent squared?
Equals 1.
1.
That's the most fundamental trig identity that you want to memorize. Sine squared plus cosine squared equals 1. And that's the entire reason that I chose to square both sides of each of these equations. Because once I square both sides of them, now I'm looking at these two equations, and I can add those two equations together to get x squared plus y squared over 9 equals sine squared of t plus cosine squared of t, which is equal to 1. So there is my rectilinear equation. That's the equation of an ellipse.
Yeah.
And this is significantly different than eliminating the parameter in most problems. In most problems, you solve for t, okay? But in this problem, that wouldn't do much good. In other words, if I solve for t, I get something weird looking. I get t equals the inverse sine of x, and over here I get t equals the inverse cosine of y over 3. Now letting this equal that doesn't progress things very far. I don't know where to go from that. So this requires that strange solution, which is to first of all get sine of t on itself on one side, cosine of t by itself on the other side, square both sides, add the two equations. Then you can switch out the sine squared plus cosine squared with 1.
Yeah.
And the same thing for a circle. In other words, if you had that, then squaring both sides would give you x squared plus y squared equals 1. The equation of a circle, in fact, the equation of the unit circle. It's a little more difficult. In other words, when it's like this, it's quite easy to see. For a long, long time, I had a real hard time remembering how to do it when it was like that. And the trick is to divide this side by 3 right off the get-go, so that you isolate sine of t and cosine of t. Now you can square both sides and add the two equations together to eliminate the trig function.
Okay.
That's a little tricky. You sure you want to, maybe you understand this, or you want to go over a different one maybe?
Can we go over a different one?
Yeah, let me make one up. And let's have you do it from the start.
Okay.
So convert that to rectangular. Remember our goal. Our goal is to get a sine squared plus cosine squared.
All right. So,
in other words, we've got to eliminate the trig functions and the t.
all right. So,
What's sine of t equal to?
sine of t is equal to 1/2 x.
X over 2. What's cosine of t equal to?
Y over 5.
Okay, now before you add the two equations together, it wouldn't do any good if we added them together right now, because we'd have sine t plus cosine t, which isn't equal to anything.
So if you square them,
There you go. What's the next step?
so it's x squared over 4 equals sine squared t.
And over here?
Y squared over 25 equals cosine squared t.
Now add them together.
X squared over 4 plus y squared over 25 equals 1.
There you go. That's the equation of an ellipse.
Yeah, I think I got it. Yeah, that's pretty simple.
All right. Anything else?
I think that's it, actually.
Okay. I did read one interesting thing about polar coordinates that I didn't ever know before, and that is that one of the advantages of polar coordinates, and I wish I could explain this further, but I can't, is that you don't have to have things be functions. When you're in XY coordinates, it's extremely important for something to be a function. And if it's a function, you can do stuff with it. If it's not a function, you can't. Well, when you switch to polar coordinates, there are no functions. Everything is a function.
Yeah.
And that solves some of the higher math problems that arise from trying to work with non-functions.
Yeah.
And also, if you're analyzing the solar system, the first people, the person who invented polar functions invented them to analyze the solar system because it works so much better. When you're talking about ellipses and stuff like that, it's much easier to analyze them with polar than with XY. Just because, I mean, the same reason that all of a sudden my thing stopped working. I guess that means that we should be done. Okay. But if I want to define a circle, I've got x squared plus y squared equals 4 in the xy plane, but in the polar, that's r equal 2. Much, much easier. R equal 2 than x squared plus y squared equals 4.
Mm-hmm. Yeah, that makes sense.
And there's also lots of other, I don't know whether you'll get into it or not, but at the end of polar coordinates is de Moivre's theorem. And de Moivre's theorem allows you to do all kinds of interesting stuff that requires you to convert to polar. Then you can do calculations much easier, convert back to rectilinear to come up with the answer. Whereas if you had to solve the whole thing in rectilinear, it would be really, really difficult to do. So converting to polar first lets you take lots of shortcuts. And then converting back to rectilinear, you get to the answer, but much faster. So,
okay.
All right. Lucas, are you good to go?
Yeah.
All right. I will talk to you next week.
All right. Sounds good.
Bye-bye.